We had been developing an ice sheet model for years, more than 15 years. And this is with my colleague David Pollard at Penn State. And we had applied the model to lots of interesting geological problems, trying to understand the evolution of the cryosphere and the ice sheets. And, with varying degrees of success. And about 3 years ago, when we were trying to replicate the really high sea levels of the last interglacial period in the Pliocene, we were struggling to reproduce those really high sea levels. So we kept going back to the physics and thinking about things we might be missing. And two things occurred to us that could be included in a continental scale model that we hadn't been incorporating yet. One of those things is the influence of having meltwater, rainwater, and summertime surface melt getting into crevasses on ice shelves with the potential to break up those ice shelves. And then we realized that if ice shelves around Antarctica were to break up, if we were to lose them quickly, maybe through a combination of the ocean that they're sitting in being warmer, so melting from the bottom up, and then this attack from above, having a lot of surface meltwater on them. If we were to lose those ice shelves really suddenly around Antarctica, where the ice meets the ocean, in a lot of places that ice is very, very thick. And so we realized that we would be exposing a lot of the Antarctic ice sheet margin directly to the ocean. And if the ice was, let's say 700 or 800 meters thick where it was meeting the ocean, in places where it has now lost these ice shelves, there would be a vertical exposure of the ice above sea level. And we know something about the strength of ice, and essentially under its own weight, that ice really couldn't hold itself together and would fail structurally under its own weight. So that was the second new physics that we added to our ice sheet model, so that the effect of the surface meltwater and then where these ice cliffs might become exposed, we added something that allowed them to retreat, like we see today in the very thick outlet glaciers around Greenland, where thick ice is reaching the ocean. And when we added these two new pieces of physics to the model, we were, for the first time, able to start to replicate some of these geological sea level high stands. And that started to give us a little bit more confidence that we were onto something. So then, we were thinking, okay, we have a model now that is beginning to be able to replicate some past sea level rise events. The model is doing a pretty good job simulating the modern Greenland and Antarctic ice sheet. Let's see what happens when we apply a future climate change scenario to the model, and we'll see what the ice sheets do. And for the Antarctic story, we got a much bigger response of the ice sheet to the kind of warming that we could see in the next century in a sort of business as usual emissions case.